In this video, it is going to be part one of a couple of videos talking about Chapter 7. Chapter 7 goes over periodic table trends, and for this video we're just going to focus on section 7.2 because it has two really important concepts in it that the book doesn't really adequately go into detail on. The first is what we call Coulombs' law. Coulombs' law. And then the second major concept that we're going to talk about is something called effective nuclear charge. And the whole real point of this section is going to be talking about the attractive forces between charged particles. Or I should say the attractive and repulsive forces that occur between charged particles. And actually many properties of atoms depend on the attraction between the valence electrons and that atom's nucleus. And in general, Coulombs' law is going to tell us that the strength of the forces between two electrically charged particles is going to depend on a couple of things. The first thing that it's going to depend on is going to be the magnitude of the charges. Okay, and magnitude is just a fancy word for saying the strength or the amount or the number of the charges. Okay, how strong are these charges? Is it going to be +3, +1? It's going to be the magnitude. Again, magnitude, fancy word just for the strength or the number. And then the other thing that it's going to really depend on is going to be the distance between the charges. Now, before we get too into detail, I just want to do a real quick overview of a concept in physics. Let's see if I can move these guys out of the way. Well, it looks like that one doesn't want to move. Alright. A concept in physics is called a vector quantity. Now, quantity just means a number, and then a vector is going to refer to the fact that it has a direction. Okay? So vector quantity means that a value has both a magnitude, or a number, and a direction. And the reason that this is important is because when we look at the behavior between charged particles, we can say that they are going to involve a magnitude and a direction. Now let's try to get rid of this stuff again. Alright. Go away. So, for example, let's take a look at the direction. We can say that if we have particle A and we have particle B, let's say they're both negatively charged, we can say that if they come into contact with each other, the force of A that A is going to exert on B is going to move particle B in the opposite direction. Okay, so the force of particle A on particle B is going to drive this particle right. And the same thing is going to happen over here. Okay, the force of particle B on A is going to be to move it to the left because these particles have like charges, so they're going to repel each other. So that's what we mean by a vector quantity having a direction, okay? Not only is the not only is the charge or the amount of charge on each of these particles going to be important, but the way that the direction that they're going to move each other in is also going to be important when we talk about properties of charged particles. So let's move these guys out of the way. All right. Now let's talk about the magnitude. Remember I said this is kind of a fancy word for strength or amount. Now, what we say is that the distance is going to matter in the attractive or repulsive forces between particles. If you have weak magnets and you're holding them, you're going to hold the plus side way over here and the negative side way over there. The distance here is so great, okay, the distance is so high that there really isn't going to be that much force. So the force felt is going to be very low. Okay, on the other hand, if you try to hold magnets really close to each other without allowing them to touch, here we have a low distance. The force that is felt is going to be very great. Okay, so distance does matter in this case. Now, let's see here. This is, if you recall from baby chem, this is called, they're inversely related. Or we could say that they're inversely proportional to one another. When one goes up, the other goes down. So, of course, we have an equation that is going to help us keep all of this stuff with actual quantities. Oh, I cannot move these guys. There we go. And that's going to be Coulomb's law equation. So here's our equation. Now, you'll see this equation written in several different ways. We've talked about the force is going to be dependent on a couple of different things. We have Q1, which is the charge of one of our particles, times Q2, which is the charge on the other. And we also said that it's going to be dependent on the distance. We're going to square that. Now, to keep all of our units in line, we're going to have a constant there, K. And our units are going to be meters. Each of these here is going to be in coulombs. And our force is going to be in newtons. And what you'll also see sometimes is that we can talk about Coulomb's law in terms of not just force, but we can talk about it in terms of potential energy. And so sometimes you will see it written as an E instead of force. And then sometimes you'll also see distance written as an R. So there are a couple different ways that this can be written. It's really all just saying the same thing. All right. So that's Coulomb's law. Coulomb's law, again, is just saying that two charged particles are going to interact with each other, and it's going to be dependent on the magnitude of the charge, how great the charge is, which is why here we care about what the actual numbers are relating to the charges. And it's also going to be dependent here on the distance, and we said that the closer they are, so the smaller the distance, the higher the energy or the higher the force. Okay, and this, to be specific here, is potential energy. Okay, potential energy. Again, like I said, sometimes it'll be written differently. Sometimes you'll see it written as a V even. So don't let that fool you. We're all just talking about the same thing. Now, I want to move on to our next topic here. Now, because most atoms have many different electrons and many protons, and from what we know from Chapter 6 about orbitals, we know that the electrons are kind of in these clouds that are surrounding the nucleus. So there are going to be tons and tons and tons of attractive and repulsive forces between all the different particles in the atom. And this is extremely, extremely difficult to actually quantify or calculate the exact values of. So what we say is, okay, let's come up with a way of thinking about how how do the very outermost electrons interact with the protons in the middle of the atom? And what we call this is, let's make it a different color. Yeah, we'll go with pink. We call this the effective nuclear charge. All right. Now, what are we talking about here? We're talking about the middle of the atom is going to have a positive charge. And we have all these little negative charges around it. We want to know, okay, what type of force, we talked about Coulomb's law, we talked about the attractive and repulsive forces between the particles. We know that the electron and electron force is going to be repulsive, but here we're looking at what is the attractive force going to be between each of these electrons and the nucleus itself, which we know is positively charged. So what we can do is we can actually count the different particles. Let's get rid of this. So for example, let's take calcium. All right, calcium is going to have 20 protons. Okay, so these are going to be positive, and it's going to have 20 electrons then, as long as the atom is neutral. So let's quick revisit a concept of valence electrons versus core electrons. So in our nucleus, we said that we have 20 positive protons. Now, in a calcium atom, let's see, we have 20, so that's going to be 1s2, 2s2, 2p6, 3s2, let's see how many, 12, 3s2, 3p6, and then 4s2. Alright, so our valence electrons are going to be the 2 electrons here found in the 4s. The rest of these, went a little farther, the rest of these are going to be our core electrons. And then just the outermost ones are the valence electrons. So we can draw this, we can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 are going to be in the core. And then we're going to have just these 2 outermost electrons. Remember, these are our valence electrons. Valence electrons in the 4s subshell. So what we can say is that we can think about it, okay, well, this one electron is going to feel the force of all 20 of the protons, but that's not actually going to be accurate. Because what's happening here is we got to consider that there's these forces going on in between here. And what we say is that the core electrons are going to have a shielding effect. Or sometimes it's called a screening effect. And what that's going to mean is that it's basically kind of protecting these valence electrons from feeling the full force of the 20 protons in the nucleus. And the way that we can calculate this effective nuclear charge, is going to be with the equation Z effective is going to be Z, which is just the number of protons, minus S, which is the shielding effect, the screening electrons. So in this case, we say that the number of total protons in calcium is going to be 20. And we say that 18 of them are going to be screening or shielding because there are 18 core electrons. And so very easily we can calculate our Z effective charge for calcium here is going to be +2. Now in reality it's not going to be this simple though, because there are actual differences within the subshells, and I'm going to post a quick follow-up to this video explaining a little bit more about that.